This next section on temperature and heat concerns the expansion of heated substances. As almost everyone knows, when things are heated, when they go to higher temperatures, because of the motion of the molecules inside, the substance expands. Now, how much does it expand? Well, let's first look at solids and look at the linear thermal expansion of a solid. What we have is we have a solid of a given length. I can draw this kind of dimensionally like this. And this length, let's say L naught, will expand when it undergoes a temperature change by an amount delta L. This is the change in length for a length L due to the addition of a temperature delta T. So when I change the temperature from one temperature to another, this substance is going to expand. And in general, this expansion is linear. Now you can kind of guess how that goes. It would go because it would go from the fact that the change in length is going to be proportional to the length. Why is that? It's because if we had something twice as long, each of the lengths would expand by delta L, giving us 2 delta L. Therefore, it must be proportional to the length. Also, if I give it twice the temperature change, I'll get twice the expansion. So it's proportional also to delta L. The coefficient of expansion, alpha, is called the coefficient of linear expansion. Coefficient of linear expansion. And it has units, of course, since if I look at this, we have a length and a length. So if I divide through by the length, it shows us that that side would be dimensionless, and this side must be dimensionless also. Since this is temperature, it must be something like inverse degrees Celsius. So this will have units of 1 over degrees Celsius. And we can look at some examples of coefficients of linear expansion. Brass is about 19 e to the minus 6. Gold is 14 e to the minus 6. Glass is 8.5 e to the minus 6. And aluminum is 23 e to the minus 6. In order to have common minus 6 units here, I did not put the decimal point between right after the first significant digit. But you can easily adjust that. And so you can see what other substances might be. You'll notice that the metals expand more than glass, brass more than gold, and aluminum even more than brass. Now that gives us our expansion. What problem might we have? The problem that you should be familiar with is you have 10 meters of gold, let's say 10 meters of brass, and you're going to raise its temperature by, let's say, 5 degrees, from 10 degrees Celsius to 15 degrees Celsius. So we're going to have a delta T that would be 5 degrees. And we would have an original length is equal to 10. What do we always want to compute? We want to compute the change in the length. The change in the length would be the natural length, 10 in meters, and then we would have a change in temperature, which would be 5, and then we would have to put in the coefficient of linear expansion of brass, which would be 19 e to the minus 6. And so what we would get here is this is about 20, so we could round that off. 5 times 10 is 50 times 20, so that's 50 times 20, that's 10, so that's 1,000 e to the minus 6. Well, that's 3 more places, so this is going to be equal to 1 e to the minus 3. And that eats up, the 1,000 eats up 3 more of these, so that's about 20. So this is a good approximation. And so you can see that it's going to be 10 meters. That's about 30 feet or 32 feet, since they're a little bit more than 3 feet in a meter. And that's going to that 30 feet is only going to expand by 1/1000th of a meter, which is a millimeter. So it's a very small expansion. So you should be able to work that problem. Now the next type of problem that you might have would be to look at how a volume, a solid or a liquid might change in volume due to a change in expansion. We have a similar equation there for how the whole volume expands. And here with volumetric expansion, we can compute that for a solid, a liquid, or a gas. And our change in volume, as before, is going to be a constant times the original volume, because if I have twice the volume, I'm going to get a change for each one. Therefore, it must be linearly proportional to the volume. And it will also be linearly proportional to the temperature. And so this equation here are two that you must remember for the test. And this is called the coefficient of volumetric expansion. And we could look at several of those, and we will in the problems that follow. And when I give you a beta, you should be able to compute how much the volume expands for that substance. You apply it just as before.